Okay, I think we should get started. Welcome to the session on learning experiences, learning tools. Number one, I think it is. So our first talk is Professor Yuan, and this is a short talk, so I think you get
10 minutes.
10 minutes plus 5, right? 10 plus 5,
Okay. So a long time ago, in my class in computer vision, I studied a paper by the person who just introduced me. And it was on parallel architectures for computer vision. And you know, when it comes to machine centricity, it's hard to get a paper that is more machine centric than that. So it's something about, tells something about our times that now we are both at a conference that's on human centricity. And by the way, I'd never met Steve before this, and I remembered the paper yesterday just by looking at his name, so there's something about me or him or his paper. So if you're going to be human-centric, you should not only understand what the human wants explicitly, but also be able to recognize some of the intense experiences that they're not articulating. And what can be more intense than facing difficulty? And that difficulty could occur with the beginning programmer, of course, trying to figure out whether they need an else or not to an if. It could occur with a more experienced programmer who's gone to the wrong language and programming in it, or using some API that they don't understand. Okay, so this is not just for students. And what we'd like to do is build a system that automatically detects if that person is having difficulty without them articulating. Okay? Why do that? Lots of reasons. But I come from a CSCW perspective, and the goal is to build a collaboration environment that communicates this information to somebody who could help, who collaboration environment to help them. So what's going to be the key to discovering whether they're having difficulty? Well, something about the developer changes that you can detect through some sensors. It could be their physical characteristics, or it could be their interaction with the computer. Okay? In either case, you need sensors, and those sensors could detect physical characteristics, but they are not common in programming environments, so we'll ignore them. They could access the programming environment commands, and actually our previous work has done that. And they could also access the web access. They could also sense the web accesses. So the question that we are trying to answer here is that what additional benefits can you get from intercepting web accesses? Okay? And this assumes that the programming could make use of the web. So we're not talking about giving somebody a bubble sort algorithm to write and say, please don't consult the web. Okay? So we are looking at some programming that intersects these two, and lots of people have looked at web-based programming. There's the cost, a talk in last year's VLSCC which figured out the cost of web page foraging, and there was another paper from that group. This morning we heard about another talk on web foraging, about a UI for it, and then there's also work done to recommend web pages that you visited before based on your history. Okay? So we are putting another dimension, difficulty, into it, and we're trying to figure out whether people are facing difficulty, and there's been work done there too. So like I said, our previous work looks at programming interaction without the web, and there's also work that looks at web-based difficulty without considering programming. So what we are doing is focusing on this area that intersection of all three circles, that what can we do here to predict difficulty. Okay? So if I'm going to answer the question about how web accesses help, I need to sort of have a baseline algorithm, and I'm going to use the baseline algorithm we had. And that algorithm is based on 4 features. It looks at your rate of edits. Okay? The more you're editing, the less likely you are facing difficulty. You're probably facing difficulty when you're debugging, or you're getting out of Eclipse, you go to the web perhaps, and changing focus ratio, changing the number of focus events. So we don't predict difficulty at each command. We divide the interaction into segments. We don't segment based on time, because if you've gone for coffee, that doesn't mean that you're facing difficulty. We segment based on the number of commands you've input, and we look at the ratio of various kinds of commands to the length of the segment. So more edits, less difficulty probably. The more the debugs, the more the focuses in and out, the more navigation, probably more. Okay? So those are the features we worked with before. And then the question was, how do we capture web interaction? And we did the simplest thing possible. We just look at the number of web pages that you access during a segment. That's the feature we used. Like I said, the simplest possible. So then the question was, what effect does it have on our difficulty prediction algorithm? And that answer depends on a task. Okay, so we had them do, appropriate to this conference, a task that required a visual user interface. And the data I'm going to talk about was gathered from 15 subjects. So here we see some of the results of comparing our baseline algorithm with the web-based algorithm. Our baseline algorithm got 20% of the positives right and got all the negatives correct. Our web-based algorithm got a much higher percent of the positives, 93%, at the cost of getting 5% of the negatives wrong. So these results seem really good. In fact, they seem too good to be true. And they are, because if you look at two different measures, we see a different story. So the true positive rate is the same as recall, and precision tells you what fraction of our difficulties were actually correct. And we got only 54% of the difficulties correct in the new algorithm, whereas in the old algorithm we had all of our difficulties that we flagged were correct. Okay. So, and the reason why precision is much smaller than the true negative rate is because only 6% of the segments were labeled difficult. That means difficulty was a rare condition, which you would expect if the programmer is doing a task that they're qualified to do. In that case, you'd expect difficulty to be rare. So one conclusion we can draw, which we haven't tested out, is that our baseline algorithm is good for distributed asynchronous help, where the cost of helping is high and you don't want a false alarm. So if I'm in the middle of making my talk and I leave it to try to help a student and that's a false alarm, next time when I'm busy, I might not even bother to try and help. On the other hand, if the cost is low, so I am in a flipped classroom and the cost of checking if a student is in trouble or not is just walking over to the student's desk, then I might want to catch more difficulties even if some of them are false. Okay. Now, what if you want one algorithm for both situations? There is this F measure that tries to combine recall and precision into one value, and by that measure, we in fact do much better in our new algorithm. Now, these results are interesting, but not that interesting because we had only 15 subjects. What's more interesting from these data is to answer the why and why not questions that these numbers raise. Okay? So let's look at a series of these questions in the next few slides. Okay. So in the beginning of interaction, there might be no web accesses, there might be no edits, and web accesses might give you an indication that there's difficulty. So that's one reason why edit is not enough and web accesses might be useful. Okay? Now, another question that arose was, why did the focus ratio not give us the information? Because losing focus could mean going to the web. As it turns out, it doesn't always mean going to the web. Okay, so that was the reason why web links added more information. Would web accesses have been sufficient? As it turns out, 17% of the difficulties had no web accesses. So the answer is no. And this is sort of the fundamental question. Why is precision decreased? So we saw that uncaught difficulties may occur when there are web accesses but no edit interaction. Okay? So that indicates that web accesses indicate difficulty. But 15% of the difficulties had no web accesses. Okay? So that's the reason why the algorithm couldn't quite make up its mind. And we try to also figure out, and that makes sense, right? Because you go to the web to solve difficulties. But the reason why web accesses also indicated difficulty was because sometimes you don't find information because of the web foraging issue. And typically we found that people would paste code from the web that they didn't understand, and that caused a lot of difficulties. Okay? Very quickly, this is a question that Brad was asking me at the coffee break. What kind of problems did cause difficulties? We didn't quite look at the edits because we don't know what the context is, but we looked at the web searches around difficulties and found that almost everything that you can think of, whether it's how to compose components, how to go and put event handlers, how to repaint something, every one of those things caused web searches that were correlative with difficulties. Okay? And so our findings are that web accesses, you added useful information, but it was a little confusing. It could go either way. And all aspects of Swing API result in web accesses. Now, what I think would be even more interesting is future work that tries to combine this various other pieces of research on web-based programming by creating a system, for instance, that recommends web pages visited previously by same or different programmers based on relative difficulties and foraging costs, and maybe provides a good foraging UI too. And let me end with Steve's. So we probably would have a difficulty detection system at the bottom, and I made this morning. And you'd have a web page recommender on the top, which would go and sort the pages by the foraging cost and provide a nice UI for actually sorting through those answers. Okay, I think I took more than time. Happy to answer any questions. How did we find the ground truth on what were difficulties? So what we had an iterative approach where every time they were using a previous algorithm to figure out what the new algorithm should be. So the previous algorithm would always make predictions and would tell them what predictions they made, and they could correct them. And also we recorded their sessions, and after the sessions we went to the difficulty points and told them, was that really a difficulty? And we also had two coders go and agree with them or not. So we had all these data together, and sometimes we use one data, sometimes we use other data, but we basically use these factors to determine whether they were really in difficulty or not. That is unlike what other people have suggested, which is every 5 seconds prompt them and say, are you in difficulty? That would be so annoying, especially because difficulties are rare. Okay? But that is what most people, I won't say difficulty, most people who want to go and predict emotions, like are you frustrated or not, they go and do such prompts. And I'm assuming that things are good normally and bad abnormally. So that's what we did. But I'm not sure whether they actually corrected the predictions. So this is all modulo our ground truth gathering methods.
Okay, thank you. Other questions? And what are the best ground truth collection methods? Can you query students? Are you having trouble right now?
That's the thing. Are you having trouble right now every 5 seconds, every 10 seconds? I mean, when do you do it? The best way I would think, and we did that too in the study, we gave them a chance to ask for help. So the researcher was the helper. So when they asked for help, we knew they were in difficulty. Though of course people sometimes ask for more help than they should, and sometimes they don't. So to me, if we just took that data, that would be the most reliable. Because we know, otherwise, what is difficulty? And difficulty we figured was we told them is making less than normal progress. So there's a certain rate, and when you know what you're doing, and now suddenly you don't. Okay, but the funny thing is that we've used the same data for many, many different exercises. It seems to give similar results. So there seems to be something fundamental here.
Cool. Great. Any other questions?
Yeah.
So in this kind of thing, do you think the precision of the recall is more important? Like, it's better to miss things or to catch them too? As you said, are you having trouble? You're having trouble, it's really annoying.
I'm all for precision. In today's world, nobody catches our difficulties, right? So if we want to improve the stability after sure. Today there's no false negatives, but there's also no true positives. So if I could have no false negatives and have some true positives, I'm strictly better than the stability guys.
So the F measure you gave then a few slides ago, what was your trade-off that you chose for using recall?
There's equal weight. That gives equal weight to both. And I would not use that algorithm for homeworks. If I'm preparing my VLSC talk and I rush out to give help to some person, they really need help, that's crying wolf. So but for a face-to-face session where I'm just hanging around and I say, my system system predicts your difficulty. Are you facing difficulty? And they say, no, what's the cost? Not much. So there I don't want to have high
Situation.
Yeah, but I'm hoping we can